Again, thank you for the opportunity to speak with you this morning, both the board and the members of the public that were able to join the presentation. My name is Josh Rupp. I'm the project manager on behalf of Colliers Engineering and Design. Our consultant team, along with OGS in the district and also the DEC, who's not on this call, has all come together. We've got a number of different types of engineers. You heard the word geotechnical engineer, that's a soils engineer. We also have hydraulic engineers, mechanical engineers, electrical engineers. I happen to be a structural engineer. I've been with the firm about 22 years, and I will quickly introduce Rex before he passes it back to me, and I'll start walking you through some of the project details.
Yes, good morning. My name is Rex Powell. I'm a civil structural engineer. I'm the design lead on this project. My background is primarily dam safety, hydroelectric, and navigation structures for, a bit over 40 years now. But I do also get involved in geotechnical, hydraulics, and mechanical designs as need be. Josh?
Thank you, Rex. For our agenda today, we've already gone through the 5 minutes of introductions at the top of the screen here, but the meat and potatoes of it is basically a project overview where we're going to first familiarize you with the site. I realize maybe not everyone from the public or the board has had a chance to see this up close, so we'll share a number of slides to show you what it looks like in its existing state, and then also share some of the work that we've put into the project for remedial measures and explain the how and why as to how we've approached those remedial measures. I realize there's an interest also in schedule, so we'll go through what our schedule is for execution of the project. Construction requirements, I'll recap. That's just basically describing what some of the impacts of the project might be, whether that's a noise, dust, water level, those sorts of things. And then lastly, I'll close out with our cost estimate, our opinion of probable construction costs, but most importantly, want to leave a good slot of time for folks to ask questions where we might have not covered something that provides an answer. So let's start off with just getting familiar with the site. This is a drone photo from above the roadway near Conklingville Dam in the background, and certainly a key feature to the site is the EJ West powerhouse. We are not doing anything as part of this project with that powerhouse, but it's certainly a notable feature at the site. Coming from the powerhouse toward us in the photo is what we'll be terming the spillway. This has a concrete cap where my cursor is, founded on a pretty large rock mass foundation. And of course, the spillway is fed by the spillway channel here, off to the left of the photo. In the foreground, and we'll be talking about this a lot, is the outlet structure. So there's a control house on top that's a pretty characteristic element of the site, and then a really large gatehouse that goes all the way down to the floor of the foundation here. The tail race is the water body in this area here. I'll be using that term through the presentation here. And then there's a retaining wall that runs along the foreground of the photo here, which works to retain the hydraulically filled embankment that's off to the right of this photo. And I'll be spending a little time too talking about this valve access shaft. We'll be doing some valve work as part of this project. There's one way in and one way out to get to those valves, and it happens to be right here. So I'll be sharing some photos of that as well. Looking at the spillway. So again, we have a concrete cap monolith structure here that sits atop the rock mass foundation. The district had a log sluiceway here that you see in the middle of the photo. That's since been filled in. As part of this project, there's a service bridge that goes out to that log sluiceway that's no longer needed that we'll be removing as part of this project. But you can see some of the conditions with both the rock and the concrete. The concrete in general at this site went through a major rehab in the mid 80s, and there are some issues with some of those concrete repairs that were done prior. For example, the concrete has alkali silica reactive nature to it, so that's something we'll be looking to address as part of this project. Looking the other way on the spillway, of course, you can see the embankment dam in the background, the outlet structure here, but more photos of the condition of the spillway. You can see some deterioration of the concrete. Again, that concrete sits atop a rock mass foundation that has a layer or a liner of gunite. You can see that here and here as well. That has some deterioration to it, and you can see some general deterioration of the concrete surfaces as we approach the outlet structure. Looking downstream to upstream now, you can see the control house atop the outlet structure. A lot of the focus of this project is on this outlet structure, which is why we want to familiarize it with you and show you the nearby elements. There's the 3 valve ports. You can see at least 2 of those valve ports are 8-foot diameter here, are an element to the gatehouse. Basically 3 ways to pass water through this dam. One is over the spillway, one is through the EJ West powerhouse, which is off the screen, and then the third way is through basically this outlet structure and these 3 8-foot diameter valve ports that you can make out in this photo. I have another photo of it later in the presentation. Of course, there's a towel race here. The access to that valve chamber I mentioned before is in this vicinity. And of course, this retaining wall is really critical to support the embankment off to the left of the photo. And I'll make mention too that this is all accessed by some stairs that come along this retaining wall area here that I'll make mention of in a future slide. Being this slide, you can see the condition of some of those stairs, which have settled over time. These were put in as part of the bridge replacement project that the county did around the year 2000. Here you can see the downstream face of the outlet structure, those 3 8-foot diameter valve ports here. There's actually a siphon system incorporated in this outlet structure as well, and the retaining wall off to the left side, and some of the condition of the rock foundation mass off to the right. I mentioned we do a home in on the valve access because that's really critical here. We need to get down to these valves. They're what's called Dow valves. They're 100 years old or very near. So they sit, if you're topside, you'd have to go down through this access hatch. You can see the blue stairs that show up in the middle photo here, and you've got to go down several flights of stairs to get basically to this room where you can see these 3 gauges here that tell us about the position of the valve, open or closed. But you can see 1, 2, 3 valves in a very confined or spatially constrained space with some mechanical and electrical components. There's also it's very wet down there, and some leakage mitigation measures that we want to incorporate in this project to help dry it out. But not a lot of room, and fairly sizable valves. They cannot be throttled. They're either pretty well full open or full closed. So the valve type also comes into play when we consider those remedial measures for the valves. Lastly, to familiarize you with the remainder of the site, there's the bridge. Again, this was replaced around the year 2000 by the county, but you can also see here this retaining wall that holds back the embankment to the rear of the photo has some concrete repair issues that we'd like to address. Characteristic to see a little bit more advanced deterioration around the bridge where we might have de-icing salts, but then also some deterioration around the monolith joints that we'd like to address. So let's talk about what our repair plan is for the project. And of course, we're pretty well through final design at this stage. The drawing you see on the screen, which I realize might be difficult to read, is a work item list that outlines everything we plan to touch or improve as part of the project. What we've done is boiled that down to the 4 primary areas that you see off to the left here, and that is there's a lot of work going into the spillway. a lot of work going into the outlet structure. And I mentioned lastly the retaining walls, and then some also work to the embankment. So I'll go through all those here as part of this presentation, starting with the spillway, which is highlighted. You can see a plan of that spillway going between the EJ West powerhouse here and the outlet structure here. There's removal of the service bridges I had mentioned out to the long log sluiceway. And then we've done a stability analysis of this concrete cap and determined that it needs anchoring in order to be more stable. So these little black dots you see along here are vertical anchors. We'd also propose to resurface the spillway, get rid of some of that ASR prone concrete that was put in the 80s and put in a more robust concrete cap. Also proposing to drill down through this cap and put in a grout curtain, which is basically, you should look at it as if it's a grout wall put within the bedrock foundation, and that is to mitigate seepage, fill any voids or fissures within the rock surface. And then there's also some concrete improvements that we are planning for both the upstream and downstream side of the spillway. The outlet structure looks like this, and this is looking from the downstream view to the upstream side of the dam. You can see the control house here. These are 2 siphon ports. This is the vertical shaft you would go down to get into the valve area, and I will zoom in on all this line work here because it's difficult to see. But basically, this is a 10 by 10 shaft where we have to get the old valves out and install the new valves. And you can imagine if you have an 8-foot diameter valve and this is a 10-foot shaft, that things are very spatially constrained to get things to fit up and down that vertical shaft. And valves are very heavy. What we're showing here pictorially that I'll blow up down in the valve chamber, here's the 10 by 10 shaft. We had to put a lot of thought and a consideration about not only how to get the old valves out, but how to get the new ones in place. We're using a gate or knife style valve that will replace the existing dowel valve. We can drop that down via crane here, but we are proposing to incorporate a trolley or a cart system to which we can move that valve body, and each valve will come in 2 pieces. It'll have the main body of the valve here, but also a bonnet that you'll see later that sits on top that allows that blade to come up vertically through the valve assembly. But once that piece is put on the cart and moved from here to here, we then are incorporating a whole overhead crane in order to move it laterally and up and down. And I want to make the point too that we can't just replace all these valves at once. We need these valves potentially to operate during the work, or some of the valves. So we'll be doing them 1 valve, then 2 valve, and then a 3rd valve in a particular sequence. And there's not a lot of space, maybe only a foot or 2 between these valves. So with the spatial constraints we have in the outlet structure, we did develop a 3D model. This is done in Civil 3D or Autodesk product. And the image to the left is a cross section of the outlet structure. We're proposing to line in, the 8-foot diameter port down to about 7'6" with what you see in gold. The replacement valve is the red assembly here, and you can see the 2 pieces to that, the lower piece and the upper piece being the bonnet, and then there's a stem that runs up vertically, and then the roof of that outlet structure is really shown to be here, and the overhead crane isn't shown in this particular image. But we're proposing a new staircase to get down into that valve chamber, an access hatch here that's updated, and then a small house structure that you could walk into to better access the valve chamber. And that's shown here as well with the image off to the right. This is looking from upstream to downstream, and you can see the 1, 2, 3 valve bodies, and there's a lot of piping and other things going on in these images, but they show the complexity of the 3D model. These are isotropic views of a similar thing. This has all These are the same image. We just turned off all the existing line work on the image to the right. But again, you can see the gold liner, the 1, 2, 3 valves, the overhead crane that is in this vicinity, the staircase, the trolley system that would transport the valve components laterally, and an access hatch here, a small hoist for servicing and getting equipment up and down, the access hatch, and then an access house here. So that's the makeup of the outlet system. So we've covered spillway.
Just pause one moment, Josh, if you would. Is that valve just a metal plate?
Yeah, Josh, you want to provide us some more details on the proposed gate?
Yes, so we have a Dow valve currently. That type of valve is basically like a butterfly valve that twists this way within the port opening, and it has a operator that works off the downstream end of that valve blade that's pulled up and down to open and close the valve. It's a bit of an outdated valve system that Dow was the individual 100 years ago that might have sold this particular valve to the district at the time. And those only really operate well fully open or fully closed. One of the advantages to this type of valve body assembly is it basically is a vertical blade that goes all the way up into this red area when the valve is open. It can be opened partially if we want to open it 50% and have, say, close to 50% flow, we can do that. So these can be throttled. They're called knife gates because that blade moves up and down within that port opening, which is the bottom half of this assembly. So it's two parts. It doesn't fit in one piece. Ideally, it would. These are specialty valves. They would probably come from overseas. I don't know if they'd be made in America even. We've been working with a European valve manufacturer in Zurich, but there may be others that, as we develop this performance spec, that take interest in this replacement valve. But it does operate a little bit differently than what's out there. It is slightly smaller than the existing valve, which is 8-foot diameter. This, I believe, is 7'6", but they perform very similarly. There's not the hydraulic restriction of having that Dow valve blade assembly in the middle of the port, so we get some hydraulic efficiency by completely moving that blade or knife up in the vertical position up here. Does that answer?
It does, thank you.
When, another question, when you pull those Dow valves out and when you put the new ones in, is that staircase going to have to be removed?
We have designed the area such that the new staircase, which is on the downstream side, it'd be reconfigured. Right now, the stairs would be closest to us in this slide. Okay, we're repositioning them in a different orientation on the downstream side of that 10 by 10 opening, and that gives us about a 5 by 10 vertical slot to drop that valve body down that is shown right in this zone. So yes, we want a safer, more permanent stair system than what's out there now. The existing one's adequate. It might meet code, but it's not very permanent either. So, and the new stairs would also help facilitate getting workers in and out of the workspace. So I think this would all go in, and then we would start dropping valve components down right next to it. Did I answer your question?
Yes, thank you.
You're welcome. So I think I'm on retaining walls. Retaining walls compared to the spillway and outlet structure are quite a bit more simple. Here we're basically proposing a reface where you see the yellow areas and address the superficial deterioration that we see. We would like to do some seepage mitigation measures along this length here, in particular this zone, similar to the spillway where we drill down through the concrete and grout up the rock mass, we'd like to do that along this retaining wall because we have a foundation interface. We want to make sure that the spillway channel isn't leaking into the earthen dam. So there's some seepage mitigation measures, concrete repair, and then of course the access improvements to address the settling stairs that I showed a photo of before. And lastly, some embankment improvements, not a lot of improvements. We had wavered in our prior studies on what improvements exactly this embankment might need, but through a lot of geotechnical, again, soils engineering, we've come up with a seepage model. This is a cross section of the prism of the dam, and of course looked at the phreatic surfaces, the flows through the dam, and have identified that we think the only improvement that we need for this project would be a relief well system. That would be at the very toe of the dam. Again, the road is here. This is the riprap along the upstream side of the dam. There's a couple access roads. So we're at the very lower access road where we're proposing to put in 5 relief well systems, and that would help alleviate some of the internal pressures within the dam. One additional thing that we're focusing on that I didn't mention in my prior slides is we're evaluating this particular zone here that you see circled, and this is a plan of course at the site in the Talrace area. You can see some large rocks in the Talrace area here. We believe they were once probably located within what we're calling a scour hole. This is not, I want to clarify, this is not a hole in the dam. This is immediately downstream, but it's in the vicinity of the dam, so we are paying some closer attention to it. It's about 20 feet deep. You can see here with some of the bathymetry. And if I were to take a cross section through the dam along this particular area, you would see this. So similar to the last slide I had, where you can see the dam is made up of different materials, whether it's rock fill, granular shells, core materials. We have a layer of fine sand that sits under this whole dam, and it just so happens that at this scour hole, the fine sand touches the scour hole, and because fine sands are a material that could be transported, we want to make sure that fine sand stays put. So we're doing some modeling. Again, we've got the 3 valves that are in the outlet structure. When those operate, they can be a little bit violent over that scour hole area. You can see some of the turbulence within this photo. And we're using computer modeling to look at the velocities when these 3 valves might be open. Now, I want to make the point that very rarely are all 3 valves open, but when all 3 valves are open, it does show a whole lot of turbulence above that scour hole area. So we're looking and using this modeling as a tool to gauge the improvement over this scour hole area. What that looks like in cross section, the valve flow would be coming from left to right, and you can see some of the turbulence, and this dashed line here represents the fine sand layer down here below a hard pan layer, and we're just looking to use some riprap improvements and doing that in a layered fashion because the fine sand can be needs to be a filtered exit from a dam safety perspective. So paying some attention to this area as we progress to design as well. Would like to move on to discussing schedule. Basically off to the left is the project timeline, off to the right denoting some risks that could potentially derail that schedule. Of course, we're working to mitigate those risks, but what we're working toward here is currently advancing a 60% set to a 100% level of design that we will be handing to the district in OGS in February. Shortly thereafter, we need to meet with FERC. FERC has been involved in the project to date. We, for example, gave them a 30% set and have been communicating with them. They have requested that we meet with them in the springtime to discuss the elements of the project after they've had a chance to review it. And we will then go through a design potential failure mode analysis. And that's just to make sure that anything we do to the dam during the remedial measures isn't posing basically any dam safety risks. Once that coordination with FERC is complete, issue final documents, go into a bid period the summer of 2026, award to a construction contractor, and then we've estimated about a 3-year duration of construction for a completion in the summer of 2029. What are some of the risks to those meeting that design schedule? Well, anything associated with a design delay, an unanticipated design issue. We think we've vetted most of those by now, given we're pretty far along in the design process. FERC review and input, again, we've involved them to date to try to mitigate that risk, but there could be something FERC brings up or a concern that they have that we have to think about and maybe alter the design. When we get into construction, there's some things we have to think about. Of course, we're not hoping for inclement weather, but this is a dam, and if we get a lot of rain, we'll have to deal with that. We have long lead items on this project. Valves could take upwards of 7, 8, 9 months to procure. We, to mitigate that, have identified that as an award submittal. Basically, we're asking the contractor when we award it to get that submittal in and get that ordered up front. There's not only the valves, but the crane. And of course, when it comes time to bidding, we want to make sure we make this an attractive contract for contractors to want to bid on. And of course, we think we're doing that, but that's, you never know or have a good gauge on what type of contractor involvement we might have when it comes time for the bidding process. And we track our schedule in a P6 schedule that you see here on the screen. The top half is more design-related tasks, and I realize it's difficult to read, but want to show you that we're putting a level of detail in the tracking our schedule here. And the bottom half is really that 3-year period of on-site construction. I mentioned construction requirements as an agenda item. What does that mean? Well, we want to do the project with a sensitivity where we're minimizing impacts at the site, whether that be noise, keeping dust down, having a lot of light. We have to comply with SWIP measures and make sure we're not compromising the water quality. We use things like turbidity curtains. So you should see some things out in the water to help protect the water quality and along the site to make sure we don't have erosion issues. We have permit requirements that, of course, we need to adhere to. That might include things like fish relocation, where we're proposing some dewatering within the tail race to work on the valves. We do anticipate some periodic roadway interruptions. For example, those stairs are really close to the road, and we might have to take a lane periodically to do some work up there, but we would coordinate that with the county during construction. And most importantly, this image off to the right is the operational curve for the dam in terms of water level. We are not proposing to change the water level beyond what we would normally do on any given year at the site. So in other words, we won't be draining the reservoir as part of this work. Things should appear in general normal. If you're on the other side of the Great Sacandaga, you probably wouldn't tell much of a difference.
Could you repeat that?
I'll repeat it. We're not proposing as part of the project to change anything outside of normal operating water level procedure.
Thank you.
Okay.
What's the definition of normal?
I know that was a big question. And of course, the goal here, you can see a photo from 2030. Here they're finishing up the project with some spillway work in the background and operating the valves for the first time. But the project completion is targeted to coincide with the 100-year anniversary of Conklingville Dam.
That was like 1930.
Yeah.
Yeah, this image is from 1930.
Very creative. I was just wondering who had a hat like this.
The board members, chief engineer in that photo.
You might have been there.
From our collection.
Sorry.
They were recruiting reenactors.
Josh.
And I'll close. This is my last slide before we'll open it up to questions here. But we're, of course, tracking the cost of all this with OGS and our other partners, DEC, the district. And again, realize we have itemized cost estimate form off to the left here, but the stuff on the right is probably the things you'd want to see. We have a base construction estimate here that we've developed. We're including what we think are appropriate levels of contingency. We have a target accuracy range that we're targeting as we approach the 100% design estimate. We're understanding the importance of a independent cost review. So we've asked another firm to have an outside that numbers to make sure they think we're on with what cost. This is a web. Means it's at a little of a higher risk of potential for cost fluctuation. We've incorporated field allowances, and those are basically allowances to try to cover costs for things that we think could be variable during the work, whether that's going a little deeper with some concrete repair, having a longer anchor because we didn't have the rock quality we had anticipated. Those sorts of things are covered in what we call cost allowances. So what are some of the risks I mentioned schedule risks, there's also cost risks. Things that we try to track there are, we've seen a lot of fluctuations in material pricing in recent years, trying to capture that in our estimate accuracy that plays in the market volatility, whether it be the valves, the anchors, the concrete, the grouting. We have a lot of those types of materials on this sort of projects. We need to keep an eye on what the market conditions are telling us for those higher cost items. And I mentioned this before, we want to make sure that we present this job to contractors in an attractive manner, and hopefully we get a good competitive contractor bidding pool when it comes time to releasing and awarding the project. So that's my summary of cost.